How are you? Good, huh? All right. We're close. It's Friday. So I'm going to finish writing up the two postulates for the special theory of relativity. Let's see. Same. And these are in your book. What's that?
Chapter 35.
Yeah, this is 35. We'll sum this one up. It takes too long. Okay. All right. I'm curious. Not knocking, just curious. Who's read chapter 35 already? Only a parts, okay. Most of you haven't even gone there. Okay. Well, let's see. I had two things to say about that type of thing. Back up. Number one, the essay portion of the homework on WebAssign, the TA and I go over those, and our comments at this point are that there's enough of you that I'm making this. This isn't all of you. Some of you, your guys' responses are excellent. But there's a sufficient amount of you that are brief. Is that nicer than saying lame? When we ask a question and then it says defend your answer or explain yourself, the point is to explain it, to show that you understand it, what you're thinking. So not even full sentences or just phrases or just saying Newton's second law. Well, that very well might be involved, but that doesn't tell us what you're thinking or how that applies. And so we're probably going to start getting a little more stringent on knocking points off if you haven't answered those sufficiently. Does that make sense? It'll help you too when you're writing the paper, because if your papers, your superhero papers, are a lot like that, the point is not to describe physics, not to make up cool stories. I mean, the bottom line is to show us that you understand at least one concept of physics, and you will need to write that in such a way to show that, yes, I understand this. This is what it is. It implies this. That means this. That's why I thought this. Show some of those steps more. So your homework can be practice for that, if you want to look at it that way. But, yeah, just a handful of you are still trying to get by with bare minimum there, and it might not work much longer. And then I can still see who's looking at the answer keys, and it's still not very many of you. I know you have lives, and it's not test time yet, but I want to remind you that it's there. A lot of people haven't even gone to see our TA. I think only 3 of you have ever come to see me. I know some of you haven't even bought a book yet. There's lots of resources for you, because you don't always learn the same way, and sometimes you got to hear it in from different perspectives, different angles. That's why I provide these. So I can teach you, but I can't learn for you. That's up to you. On that note, an exam is close though. Next Wednesday, which has been listed all semester. So your homework 7 on chapter 10, projectile motion, and chapter 35, relativity, will be due Sunday. We'll finish relativity up today, or enough. Monday we'll review for the exam. So it would behoove you to go over to some of the homework maybe this weekend, or at least some of the parts you didn't understand. Come with questions so I can help you. And then the exam will be next Wednesday.
And the exam covers everything.
No, not the stuff from the first exam. So that one is just chapters 6 and 7, which was momentum and energy, and 10 and 35, projectile motion and relativity. So the stuff we did 1 through 5, Newton's laws, won't be on this exam. The final will be comprehensive, everything, but this exam is just the last stuff since the first exam. Did you follow that? Okay. Well, you know what? Let's look and see. I wasn't planning. When is your first superhero paper thing you do? There it is. March 13th. So that's in 3 weeks. I'm requiring, well, any time up till then, but after that you're going to get docked points. A superhero paper idea. You just need the idea, as explained in the instructions on WebAssign. So you got about 3 weeks to come up with what you'd like to write about. Yes?
Do we have to email you the idea?
You can come tell me. You can write it on a piece of paper. It was like the title, the main principle you're doing, and enough sources to see that you're not just making this up. You'll have a place to go. Some people go, yeah, I'd like to do it on, I'm going to do Newton's third law. Okay. Have you looked to see that you'd be able to use something, find it? You know, I just want you to have done a little search so that you're not thinking that, and then it becomes right before the draft's due, and you go to look, and there's nothing you can find, and you're hosed. So, this should be the easiest step for the paper. Reread the instructions, see what's required. That's March 13th, 3 weeks-ish. Okay, let's have fun with relativity. So, from our last discussion, last lecture, and that video, we learned about frames of reference, that motion's all relative. Because there's no fixed absolute frame of reference from which we can refer to everything. Wouldn't that be convenient? That's what they thought way back when. A lot of people thought it was this thing called the ether. Sound requires a medium to travel through, like water or air or some solid material. They thought light also required a medium. So like the light from the sun, like it had to travel through something to get to us. They didn't think it could travel through empty space. So they called this thing the ether that it traveled through. And they were trying to measure with respect to that. They figured if anything's an absolute frame of reference, it was that. So light, they thought light was relative also. And I mentioned, and it's in your book, explained better than I did, the Michelson-Morley Experiment was a pivotal point. They were the last names of two scientists, and they went out to prove this ether existed, and that light was relative. So as the Earth moved through space in one way versus the other, they figured light would add on or subtract to that speed, and they could measure that difference. They did it very sensitively with light interference, which we will study later, which works on very, 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 very small scales. And they came up with a null result. The speed of light, every time they did it in every direction, was absolute, was the same. So in a sense, it was a major failure. But we built on that, which is why it was so pivotal. Einstein took it further, and one of his postulates then, okay, we accept this experiment. Other people tried to do it and have been doing it ever since. And ever since, we have found that the speed of light is a constant. I'm summing it up. Technically, it is the speed of light in free space has the same measured value for all observers, regardless of the motion of the source or the motion of the observer. So whether you're staying put or moving around, everybody measures the same speed for light in free space. We will learn it slows down when it goes through air or water or glass, and that's how it bends. It's called refraction, and that's how we can focus and see things. It's because it slows down slightly. But everybody would measure the same speed in glass, whether they were at rest or moving. The speed of light is a constant. It doesn't add and subtract to other velocities like we're used to with physical objects. So that was one postulate Einstein went with. And the other was Well, since no frame of reference is special, if you're in a uniformly moving reference frame, things are normal. You can't actually tell you're moving. Remember, that's like throwing the ball up and down here. Or on an airplane, it still goes straight up and down relative to you. If you had nothing to reference it against, you wouldn't know whether you were moving uniformly or at rest. It's only when we compare it to something else or have the background or something. I do want to emphasize uniformly moving. That differentiates the special relativity from general relativity, which is the last chapter in the book, and I've chosen not to go there. But you're welcome to read it. It's great. We can discuss it if you like. But I'm not going to cover it in the course. That means you're moving at a constant speed. If you change your motion, change your velocity, you're accelerating. That's when the general theory of relativity comes into play. And there's lots of cool results from that as well. But Einstein based it all on these two things. Given this, some funky things come out of that. Yeah.
So is light the only thing that we know of that is constant like this?
Yeah. Light seems to be the only thing that's constant like this, especially with motion. Scientists have these fundamental constants, for the universe, for values, but yeah, the speed of light is one of those. The others are kind of more abstract and arbitrary. But I would say, from what you're implying here, absolutely. Because all other motion seems to add, subtract to things. Light, everybody measures the same speed, whether they're moving or not. That's one of those theories. It's called a theory. And you've learned what a theory is. It's a bunch of facts and laws and principles put together that have been tested over and over and over again, and it describes the natural world around us, and it's working. And nobody's been able to prove it wrong yet. If they do, we'll adjust it by all means. Yeah?
What's the difference between a theory and a law?
Theory and a law. That was back in chapter 1. A law is, let me give it to you the way they say it so I don't confuse you. I'm just going right off the definitions here. Law, or principle. General hypothesis or statement about the relationship of natural quantities that it's been tested over and over again and has not been contradicted. So it's about one specific thing, a general hypothesis or statement that's been tested and checked. Where a theory is a synthesis of a large body of information. It encompasses several laws and principles and well-tested hypotheses. It's a bunch of things put together. So a fact is like one individual thing. The earth is round. Fact. A law is like Newton's first law, second law, third law. And that principle has been tested over and over again. You could put the laws together with the forces in motion and make up this theory. It doesn't have a name, but that's an example. So the special theory of relativity is putting together several of the laws. There's obviously a lot more to the special theory of relativity than we will get into in this class. Does that help?
Yeah.
Yep. Yeah, everybody will measure the same speed of light through something. They'll get the same value. They're covering their heinies because in free space everybody gets the same value, period. But light does actually travel slightly more slowly in glass than it does in air or free space. But if I'm at rest measuring that speed through here, I'll get a certain value. If you were traveling around on a spaceship and you measured the speed of light traveling through there, you'd still get the same value as I do. That's what it's implying there. Yeah?
What if you had two bodies both moving at the speed of light going like opposite directions?
Two bodies measuring the speed of light going away from each other or towards each other or like this. They would each still get the value of c for the speed of light. They call it c. Yep. They don't add or subtract like we would like if you were throwing a ball or shooting a missile or something. Weird, huh? So he based it on this assumption, based off of Michelson-Morley Experiment and a couple others, but now nobody's ever contradicted that. So yeah, everybody. So yeah, even if you were going the speed of light and you turned on a flashlight, right? You think, the beam of light. Well, wait, you're traveling at the speed of the beam of light. You think you just stay with it? You wouldn't. You would still measure the speed of that light coming out of the flashlight as c, this value. Speed of light. It wouldn't mean it's going twice the speed of light because you're going the speed of light and it's going the speed of light. It doesn't work that way. I can't tell you why, but that's how it is.
But to someone watching, would it look like the light's going twice the speed of light?
To someone watching, no. Like us watching somebody on a truck or a train go by and yeah, it would look like it's going twice as fast. No, we would still get the speed of light. They would get the speed of light. And someone whizzing around in a spaceship looking at both of us with our flashlights would still get the same value. This is one that's kind of blah, 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 and we're not used to that. So given that, let's see what these funky things are. I'm going to start with a little video. Simultaneity is one thing. It's just a couple minutes. All right.
Imagine one seated in the center of and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to speed.
That makes sense, right? We're still good? See, distance, time, you got everything you need to know to understand the special theory of relativity in its fundamental form here. So yeah, that makes sense. Same distance, the wave took the same amount of time to travel to him. Okay.
The speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. Predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train...
So the one that happened at the front of the train, see, both bubbles are about the same size. Light has the same speed. It's traveling the same distance in the same amount of time. But the train's moving to the right at the same time, correct? So if that red spot is where the person's sitting, the light from the front of the train should get to them first because they've moved into that wave. Where the one in the back will take a little longer because you're like running away from it. That's the idea. That's what the guy on the platform predicts.
The train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicts, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein, flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
So yeah, people can disagree on the timing of events if they have relative motion between them. I can be moving with respect to you, or you can be moving with respect to me. I could be at rest, you could be at rest, one of them, or we're both moving together. As long as there's relative motion between us, we don't have to agree on simultaneous events. Like the guy on the platform would swear, and he's right, that they happened at the exact same time for him in his reference frame. That's true. But the person on the train saw the front one strike first, can prove it, and is correct. For her, it did strike first. It wasn't just a perspective thing. It really did. I like thinking of this when I'm watching Star Wars or Star Trek movies, you know. Spaceship traveling on. They fire. Okay, you're at a standoff, right? Star Trek like to do this one. Don't fire until you see the whites of their eyes. You know, the Klingons, wait. And then, boom, they see them fire. So they fire. Well, if there's relative motion between you, you could totally disagree on who actually fired first. And both be right. So no wonder there's wars. But no. You know. So that's one consequence. They're both using the same laws of physics. That's postulate number one. If you're moving at a uniform speed, like we had in that example, they used physics that you know to justify it. She's sitting in the middle of the train, so it went the same distance. If it's traveling at the speed of light, the only way she can say that one, why she sees that one first is because it happened first. Because it doesn't travel faster from the front than it did from the back. It's the same speed of light. They must have happened at different times. What do you think of that? Good? You're going to have to chew on this stuff more. Again, if you haven't been reading the text up till now, which I hope you have, at least read this one. Okay, another one.
Like when something happens and there is a bunch of people watching the same event, everybody has their own version.
If a bunch of people are watching the same event and there's relative motion between them, they can definitely disagree on when the things... We're all at rest with respect to each other. So we're in the same reference frame right now. So we would all agree on events. But technically, I'm moving now, and there's relative motion between you and me, so we could disagree on when events occur. Technically, there's a slight difference. Now, we never notice this stuff until you're going at relativistic speeds, which means really fast. They generally don't worry about relativity until you're at least going 10% the speed of light, which is fast. That doesn't mean it doesn't apply to us. What we deal with are Newton's laws. Newton's theory of motion and everything we've had applies at slow speeds. It's like an approximation. It works. So why get complicated with special relativity? Special relativity works at our slow speeds too. But we don't need to get that complicated with some of these formulas that I haven't shown you yet. So special relativity is more generic. It works for all speeds up to the speed of light, where Newton's laws work for slow speeds that we deal with in everyday life. But when scientists have to deal with satellites whizzing around the Earth in an orbit, or subatomic particles that are cruising really fast, they must consider special relativity to get the answers right. Or radioactive particles even works. Does that make sense? So Newton's laws are kind of just an approximation, a special case at slow speeds. Special relativity extends it up to the speed of light. So Einstein realized then, if this is all true, we're making these assumptions. The speed of light, c. That's a velocity. Remember, velocity is distance over time. It's how you change your position with time. You realize you cover a certain amount of space in a certain amount of time. And that's what you'll see in one reference frame. If you're in a different reference frame, moving relative to that one, you might be covering a lot more space, right? but you both agree on the speed of light. That's the one absolute between reference frames. It's the same for everybody. If that's true, what's this person's time need to be? The way I'm drawn anyway, if you got less space and less time, big space, there'll be more time to keep this ratio the same. If someone thinks they're covering more space, it'll take longer to do it at the speed of light. Somebody that's less space, it'll take less time because you're still getting the same speed for light. That's what those two people could do, and they'd agree on the speed of light. But the one in the train, time would dilate or slow down. Time dilation, it's called. That's usually the big one that people like to quote with special relativity. For this person, it'll take longer to do certain things. It's like, and it's not just clocks. It's everything. Biological clocks. She would actually age less, age more slowly than the person that's at rest relative to that person. Time dilation stretches out. Now, neither person notices this about themselves. Person at rest, things seem normal. All laws are the same. You go about it. The person on the train or the spaceship going near the speed of light, things seem normal. You can still toss a ball, right? It comes right back down. The laws are the same. You don't feel like you're aging more slowly or that it takes more time for the ball to go up and down. For you, it's normal. But if this person at rest is looking at that person, to this person, their time is moving more slowly. And since motion's relative, you're over here. You don't know whether you're moving at a uniform speed or at rest. And you look over at that frame of reference, that person looks like they're moving relative to you, correct? If you had no reference points and all you could see are the two people, this person could be moving away from this person, but it looks like, so this person, it looks like the person's moving away. This person, it looks like this person's moving away. Motion's relative. So from this frame of reference, it looks like that person's time is moving more slowly. And they're both correct. Because motion's relative and the speed of light's a constant. So Einstein wrapped this together. You can't really separate space and time. It's kind of like space-time. You've probably heard that before. How did he word that? I like how he did it. You can meet again in the same place and space, only at the expense of time. It's like time is another variable anymore. And so not only can you see the time slowing down, but it's intertwined with space. This ratio has to stay the same. So another way you can look at it is if time's slowing down, maybe you had less space. Get the shadow out of the way for you. So another thing is length contraction. These are the two funkiest things for me. Length contraction. So again, if there's relative motion between reference frames, each one thinks the other's time is running more slowly because they're moving with respect to them. Things seem normal to themselves. But another way to justify this is their lengths could contract. If this is at a fixed speed, maybe they have less distance to cover. It's not just maybe. Einstein says that's what it is. For them, they do have less distance to cover. So it's as if lengths contracted. That means, let's take this. Let's say this is a foot long. We're all at rest with respect to this. So if we take our measuring stick and measure it, we get a foot. But now I hop on a spaceship and cruise at 80% the speed of light, right? Now we would disagree on its length because there's motion between us. What do you think I would measure it to be? What do you think? Smaller, because I just said length contracts. That only happens when there's relative motion between you and the object in question. Very good. It would be shorter to you because we're in motion relative to each other. This is moving with respect to you. And so if you were to do some experiment to measure this on my spaceship moving with me, you would measure it as less than 12 inches. But I'm at rest with respect to it. It's moving with me. So I would still measure it as 12 inches. Does that make sense? I mean, maybe not, but what I'm... Theory of relativity might not make sense, but what I am explaining, does that make sense? Yeah. Very good. Yes. Yes. Let's say you have one also, right? There you go. You guys are at rest. So if I'm moving, now that looks less than 12 inches to me. But it looks 12 inches to you because you're at rest with respect to it. Because it's relative. It goes both ways. So also, I'm moving. I have to turn around, but say I just keep going. To me also, it looks like time is slowed down for you guys. But it's still the same for me, because in my reference frame, things haven't changed for me. But the reverse is true. It looks like my time is slowed down to you guys, because I'm in motion relative to you. Thanks. So, simultaneity, when events happen, most people disagree with uniform reference frames moving with respect to each other. And also you get this thing called time dilation and length contraction. By the way, length contraction only occurs in the direction the relative motion is. So if I'm moving like this with respect to you, it looks like it shrinks in this direction, because that's the direction I'm moving. It would still have the same width, because I'm not moving towards you or away from you. If I went off at an angle, then we'd have some contraction this way and this way. Does that make sense? Let me show you another little animation. Your author made this one. Okay, so it's a light clock. Einstein thought of this, and it's basically just a pulse that goes up and down here on the top one. Just focus on that one for now. So it goes up, travels back down. It's like mirrors. It took a certain amount of time. This tells us it took 4 nanoseconds at the speed of light. 4 nanoseconds. But the one on the bottom, let's do it again. It's moving at 1/10 the speed of light. So 10% the speed of light. Pretty zippy for us. Notice it goes up and back down also. But the ship is moving, translating horizontally. And so for us looking at it, the light looks like it took that path, the diagonal path. Right here. And that diagonal is a little longer than if it just went up and down. Remember, if you're on that ship moving, what do you see the light do? If you're on the ship, traveling with it, what does the light look like it's doing? Straight up and down. Just like the top one here. You don't know if you're at rest or at uniform velocity. But if we're looking at it, it looks like the light travels this path, which is a little longer. How can that be? If light is fixed and travels at the speed of light, that can't change. Has a fixed velocity. How can it travel more distance? Well, the idea is either that distance seemed to be contracted for us, looking at it, or it had more time to do it. Actually, it's both. You got length contraction and time dilation. This is a simulation, but it's using the formulas of relativity. And you can see that it took 4.1 nanoseconds to do that. The theory of relativity predicts that it would take 1/10 of a nanosecond longer for the light to do that from our perspective, from our frame of reference. So it looked like time slowed down for us looking at them. Let's go faster. If we're going half the speed of light, same idea, but it becomes more conspicuous. Now it looks like it traveled even further. It took 4.7 nanoseconds. And if you're going 90% the speed of light, theory of relativity says, look at that, the top one made it up and down before it looked like the moving one ever reached the top. It took over twice as long to get there. If you were riding on that ship, to us here back on Earth, it's stationary, we would think your time has slowed down. You would age nearly half the rate that we age at. Have you heard of the twin paradox? There's a great explanation. It's one of the best from our author in the textbook that even proves it and justifies it. Shows you with things of light and whatnot. But the idea is just this. And it's all based on these two postulates, two assumptions. So, if the person in the spaceship is moving, it's like you start out with two twins. Yeah, I'm getting into the story. It'll probably be a bit. Go ahead and ask your question.
I was just going to say, is that why so in the movie Interstellar, is that why they're like in different planets? The time is different. They're just on Earth, like 3 hours on.
Yeah, who's seen Interstellar? A fair amount of you. Yeah, they employed relativity. Yeah, they employed it more because of general relativity, which has to do with them accelerating, and also gravity. When you get closer to a black hole, a planet that's closer to the black hole, there's a stronger gravitational field, and that warps space. Space is intertwined with time. This ratio still is constant. So if you're warping space, you also warp time to keep that ratio the same. That's the idea behind it. You get closer to a black hole, people that are under a stronger gravitational field, the general relativity basically says time will run more slowly for them from our reference frame. For them, it seems normal, just like in Interstellar. It seemed normal to them, but they came back, right? That's like the twin paradox. Wait a minute, you start out, you're all the same age, and then one of you travels at the speed of light, or, in Interstellar's case, increased your gravitational field. It seemed like it was just days or weeks. I don't remember on Interstellar. You come back home, or back together. Now you're in the same reference frame, at rest with respect to each other. And wait a minute. The person that stayed put is older. And you both agree on that. You don't while you're traveling, if they could see. But once they get back in the same reference frame, one of them's older. Because time traveled more quickly for them and more slowly for the other. And it seems like a paradox. To emphasize the paradox part, let's just take the twins. One stays on Earth, one goes flying on a spaceship. This is the example in the book. Well, the one on the spaceship seems to be aging less quickly, more slowly to us on Earth. Right? According to what I told you so far? But what does the one on the ship think about the one on the Earth? They don't see them aging fast because motion's relative. If you're on the ship, what do you see? You see the Earth receding away from you at 80% the speed of light. The Earth sees the ship receding at 80% the speed of light, right? We see that receding at 80%. It's like we're at rest and they receded away from us. So the people on the ship see the people on Earth's time move more slowly. They think they're aging more slowly. They think they're aging more slowly. That's the paradox. Who's right? They are both right at that moment. Any test they could do, that would be verified. When the person gets back, though, they're both in the same reference frame again, and they both agree that the one that stayed on Earth aged more. Does that mean the person on Earth was wrong? Well, the short take of the story is the one on the ship wasn't always in a uniformly moving frame of reference. You had to accelerate to get up to that speed. Now you can be at a uniform speed, but they had to slow down to stop and accelerate to speed back up the other direction. Now they can travel at a uniform speed. Then they had to decelerate to stop and get on Earth. And those reference frames where it wasn't uniformly moving, where it was accelerating, that's when you have to employ general relativity, and it still agrees. But that's the difference. The people that stayed on Earth never had to change reference frames. The one on the ship did. And that's why the one on the ship seems younger than the one on Earth. Yeah, if the ship really stayed put, say you're a third party watching this, right? From a third reference frame. Yeah, if the ship stayed put and the Earth went off, turned around and came back, absolutely, it'd be the other way around. So the paradox is that while they're both moving uniformly relative to each other, they disagree on whose time is moving more slowly. Just like we would disagree on whether the eraser was contracted or not. It's not contracting to me, but yours is to me. But mine is to you, and yours isn't to you. It's all relative. But it makes cool movies like Interstellar. Who's read Ender's Game? Like that story? I don't want to give things away, but basically the gist is they're fighting aliens. This one guy was able to do it without luck, so he had the knowledge. But they were trying to get it to this new person that was going to end up, being the hero. That part's obvious. Well, he gets trained by the old guy. And at one point, the new guy says, wait a minute. You did all this, history. Wait a minute, you should be dead. That happened like 70 years ago or something. And guess what the explanation was in Ender's Game?
What is the name?
Ender's Game.
It's a movie?
It's a movie now. It started out as a book. But the way they justified it in the book and the movie was the special theory of relativity. Basically, they took the old person that had the knowledge, and they knew he needed to train the young person if they were ever going to survive. But if they took the time to bring them together, he would have died. It takes too long. Interstellar travel. So what did they do? They got him on a ship that was going near the speed of light. For 50 years? I can't remember. Who read the book? He said it was an extremely boring voyage. That would be. But the idea is his time, he aged more slowly relative to us. So when they did get back together, he was still alive and could train the younger generation. It's, the nerd in me. I looked up the values. Let's see. If you want to look it up. Yeah, he was gone for 50 years. So it was 50 years for the old guy. It was only 8 years for the new guy. That ratio is 6 1/4. 6 1/4. That's a factor I'm going to tell you about now. That's the factor of time dilation and length contraction. And if you figure out how fast he had to have been going on that spaceship with that factor, he had to have been going 98.7% the speed of light for that to have worked in Ender's Game. And we can figure that out with special theory of relativity. Let me give you that formula. I want this one. There's a factor. It's called, the Lorentz factor, because this guy first figured it out. It's represented by the Greek symbol. I just brain lapsed what that is. That's gamma, yeah. And it is 1 over the square root of 1 minus the speed you're going squared divided by the speed of light squared. So this is your velocity, or the relative velocity between reference frames. So if I'm going 98.7% the speed of light, that's this velocity right there. You can plug that in. Or if you know the factor, 6 1/4, you can solve for that and get 98.7% the speed of light. No, I'm not going to make you do this, but that's the critical factor in special theory of relativity. What's nice is you can just do this ratio. I made a little graph to give you an idea how this works. I think it's in your book too. So let's say this is the Lorentz factor. If the Lorentz factor is 1, that means you are going, right here, 1/4 the speed of light. That's your velocity. So you'd have to be going 25% the speed of light before this Lorentz factor was ever... No, I didn't say that right. It's 1.3 at that point. It's just above it. So it's essentially 1. So you can see, we don't see much effects because the factor is 1 to 1 until you're going really fast. That's my point here. If you're going less than this, if this factor is 1, then everything's the same as far as we know. The formulas work out like this. This is the time at rest. If the Lorentz factor is 1, then somebody moving slowly gets the same time. But as you go faster and faster and faster, the Lorentz factor increases. That's the way that works. So as your v gets bigger, so will the Lorentz factor. And if this is more than 1, can you see that this time will be bigger? The time interval is longer. It's as if they have more time to do stuff. Their time slows down. That's time dilation. And it's this simple. It's just by that Lorentz factor. Length does it similarly, like this. So if the Lorentz factor is 1, no difference. We agree. But if you're at rest and the Lorentz factor is bigger than 1, say it's 2. Say the Lorentz factor is 2. How much shorter does the object look? By a factor of 2. It's half the length. It's contracted to half its size. If your Lorentz factor, which gives you an idea of how fast you're going, is bigger than 1. Specifically 2 in that case. And if the Lorentz factor is 2 here, you have twice the time. Time is running twice as slowly for you. So for the Ender's game example, if that were real, the Lorentz factor was 6 1/4. So time was slowed down by a factor of 6 1/4. Lengths were also contracted by a factor of 6 1/4. This works out like, looks something like this, where you're approaching the speed of light. If you're going half, let's see, not this, then this is still only like 1.15. If you're going 3/4, you've made it to 1.5. So still, you're going super fast, and the Lorentz factor is still only 1.5, so you don't see much of an effect until you're really cruising. But once you approach the speed of light, see how it goes up exponentially? We were, 6 1/4 up here at 98.7% the speed of light. Now things are stark obviously different.
Professor, that little circle next to time, what that means?
Oh, this? It's to distinguish between the two times and lengths in the different reference frames. The one with a circle is referred to the proper time or the proper length, which is the one at rest, when you measured at rest with respect to you. They did this. They took a clock. I'll end with this. And I'm at rest with respect to it. So I get this time. It's running at this time. And then they put it on, I think they had 4 clocks. And they put it on airliners, jets, and we went around the world a few times in different directions. So you're at relative motions with respect to each other. The time of dilation on the airplanes is this one, with respect to the one at rest. And you know what happened when they got all the planes back together in the same reference frame at rest with respect to each other and compared the clocks? They were different. The ones that went whirling around the fastest were running more slowly. They were behind the other ones. And by how much? This exact amount. That was one they proved. They justified the theory of relativity again. It works. Nobody has disproven this yet. Chew on that over the weekend. We'll do a little more Monday and review for the test.